Hello, everyone. Welcome to our MCIT Online admissions video. My name is Olivia Roth, and I'm the Associate Director of Student Affairs for MCIT Online. And I'm going to let our guest introduce himself, but we're going to do a little bit of a different format this time. We're going to start with actually a presentation on a computer science topic that is very timely issues of our day. And then we'll have a little bit of time for questions about the presentation afterwards. And then we will do more of a general admissions presentation and have time for questions about that as well. So just a general note that if you have questions along the way, Zoom has a feature that is a special Q&A tool where you can put in your question there, and then not only can typically other people can vote for your question so we can see which one is the most popular, but then also my staff can answer some of the questions in real time if it's something they can easily answer. So we're again going to start with our presentation. So take it away.
Hello, everyone. My name is Sampath Kannan. I'm currently a co-director, faculty co-director of the MCIT online program. So we are making lots of decisions about admissions and curriculum and what the contents of courses should be and so on. I'm also a former chair of the computer science department here. And the reason we picked this topic, first of its kind presentation where we're going to talk about research first. The reason we picked this topic, as Olivia said, it's a very timely topic. But not only that, it's also the topic on which most of my research happens these days. And not only that, it also happens to be the topic in which Penn is a world leader. So I think for all these reasons, it seemed appropriate to talk about big data, the good, the bad, and the ugly. And if you're old enough to remember the movie by that name, The Good, the Bad, and the Ugly, you can play that theme music in your head. It's pretty unique piece of music.
Unfortunately, still copyrighted.
All right, what do we mean by this? Great. Okay, so let's talk about the good first, as the title suggests. Lots of benefits of big data. What happens with big data is that we have personalized data about each individual, and therefore makes it possible to prescribe medications and treatments that are personalized to your particular data. So for example, if several people have, let's say, God forbid, cancer, you might look at the genomes of individuals, you might look at their past medical history, their family's medical history. All of this is data. And then there's something called machine learning that goes on top of it that figures out what's the best treatment for you. You're probably familiar with things like recommendation systems, which pop up, sometimes annoying, but sometimes scarily appropriate ads about what you should be buying next. So these are recommendation systems, or what music you should be listening to, or what movies you should be watching. They basically use all the data about your own browsing habits, but combine it with data about like-minded people that have similar browsing histories and make recommendations based on that. More seriously, big data has been a huge boon in disaster relief, mapping areas that have been hit by a disaster, finding survivors based on various kinds of sensor data or other data, and then putting it all through machine learning again to figure out where the maximum help can be given. Most exciting and maybe a little bit futuristic still, although there are pilots underway, are these vehicles that will drive themselves. You've heard of Google doing this, and other companies doing it as well in Arizona and other places. This could very well be a technology that's commonplace in 10 years. And what makes all of these things possible is machine learning. So let me tell you briefly what machine learning is. If you imagine a standard old-fashioned way of how decisions are made, and the kind of decisions that machine learning is particularly good at is something called classification or binary classification. Basically, imagine a bank loan officer sitting there looking at a loan application, which is just data, and making one of two decisions, either to approve the loan or to deny the loan. So you can see that bank officers taking into account all the data in the application and then saying approved or denied. So in a sense, the bank officer is acting like a classification algorithm, classifying people into those who get the loan and those who do not. And it's called binary because there are only two answers. Now, in machine learning, what happens is that there is an algorithm that's watching the bank officer for a while. So basically watching the data that's coming into the bank officer and watching what decisions the bank officer makes. This is called the training data for the algorithm. It's basically learning from what the bank officer was doing. But after it's seen enough of these examples, it just displaces the bank officer and takes over. And so now it's processing applications based on the knowledge it's gained. So somehow it's able to generalize from the examples it's seen what's the rule for deciding who gets a loan and who doesn't get a loan. That's, in a nutshell, what machine learning is. And this is one example of learning. It's called supervised learning because the bank officer was providing sort of supervising input saying this loan should be approved and that loan should not be approved. So that's called supervised learning, but there's also unsupervised learning, reinforcement learning, active learning, and many other branches of machine learning. It's such a big field. It's almost its own department in some universities, not just part of computer science anymore. I mean, although it continues to be part of computer science in most universities. Okay, what is this recipe? I mean, this sounded like a little bit of a black art, the way I described machine learning, but what does it take for this process, for the algorithm to really learn the rule that the bank officer is using or it should use? Well, first thing is that it should have as much training data as possible. The more data, the better. That way it really gets a full picture of what causes a loan to be approved. And then it needs to know which are the pieces of the data that are worth focusing on. So for example, on a loan application, whether a person is left-handed or right-handed may not matter so much. That's an irrelevant feature. Whereas how much money they make per year, that sounds like a more relevant feature. So it needs to pick what are the relevant features in each application, and it needs to pick those features carefully. And it should find a classification rule that's appropriate for the task. I mean, I don't want to elaborate on that. That's a pretty mathematical notion, what is appropriate for the task. And the most important thing about a machine learning algorithm is that the classification rule it produces should be reasonably simple. If you produce a very complicated rule, and I've illustrated that by this Rube Goldberg device for a napkin that wipes a person's face by a crazy contraption, that kind of algorithm is not what we want. We want a very simple algorithm in order for it to generalize to new data pretty well. Okay. So that's the good. Machine learning is this technique that has really come of age and it's being used all over the place to do good to humans. Now, the bad is the concomitant loss of privacy that happens with the use of machine learning. And you've all seen headlines about data breaches where stored credit card and other information has been compromised at various vendors, about fear about Big Brother governments having too much data about you and maybe monitoring you closely. That's always a concern for certain groups, especially. Let's do that. Come back there. And one big headline recently was that Amazon's India data was exposed recently and showed off sellers' financial data. So this is just one example of a recent headline, but there have been many, many. So what do we do about it is the question. First of all, let's understand the problem. As I said, machine learning works better if there's more data, but more data means more potential for privacy loss. So what do we do about it? Well, one thing that was tried in the early days was this idea of anonymization. What do we mean by anonymization? Basically, you store the data, but strip any identifying information about the individual off the data. So maybe you store what movies a person watched, but don't store the person's name or social security number or anything like that along with that. So maybe you anonymize like this, but unfortunately, this turns out not to be good enough. In fact, machine learning can reconstruct the data that you stripped off based on other surrounding information. And there was a big finding of this kind. Two researchers found Narayanan Shmatikov, found that supposedly de-anonymized movie review data at Netflix was again identified with people by relating it to data at another movie review website called IMDb. So this kind of matching can be done by machine learning algorithms. And so anonymization is not the answer. So the other thing to note about privacy is that nobody, not any of us, I think, should want privacy absolutely. Because that means if you really want not to share your data at all, then you don't get medicine that's exactly tailored to you. You don't get all the benefits of machine learning that you want. So you really want to be willing to trade off a little privacy and get a little value out of it, but you need to be in control of this process. So that's really what we want. We don't want to absolutely guard our privacy, but to balance it against the value. And to get that, we need better laws, better security, but we also need to quantify how much privacy we are losing and how much benefit we are getting. So we need a notion of how do we quantify the loss in privacy in a certain action? So that's the question. And there comes mathematics. So this is what makes it interesting to computer scientists like me. Privacy sounds very difficult to quantify. It sounds like a social and legal concept. But one of the amazing things about computer science these days is that it has found a way to quantify things that nobody thought could be quantified, privacy being one prime example, and fairness, which I'll talk about, being another. So how do we hope to quantify privacy? So in the last 15 years, there's been one particular definition of privacy that has taken hold. And it's now so popular that Apple and Google and everybody else is implementing it. But it's a very mathematical notion. And it's called differential privacy. And what it is a measure of how much you're compromising privacy. And I'll explain how in a minute. Suppose you have a database of people and their salaries, let's say. And let's say one individual in the database is Tom, and he makes $50,000. That's one item in the database. And somebody who wants to learn something about this database makes a query. And the query, the response is not going to be a definite one, but it's going to be a noisy one. That's the picture of the coin tossing. So the database is not giving a precise response to protect privacy, and it's going to give some kind of noisy answer. Now imagine that the same query is made to a database which is exactly the same as the previous one, but does not contain Tom. So basically the only difference between the two databases is that Tom's data is missing in the second one. And the same query is made and some randomized answer is given. We'll say that this process of giving the answer is differentially private if the result from result one and the result from result two are very close, meaning most of the time there's the same probability of producing the same result in both cases. What that means is that Tom's data didn't really matter in terms of affecting the result too much. One person's data does not affect the result too much. And we can actually measure how much the results differ when Tom is in the database and when Tom is not in the database. And that is the loss of privacy. That measure of how much the results can differ in the two cases is a way to talk about the loss of privacy. And differential privacy uses this idea and then asks whether we can do many things that we would want to answer from the database in this kind of private manner, where changing one individual's data does not change the result too much, change the outcome too much. And there's a huge literature now in the last 15 years on what problems we can solve in a differentially private manner. And Apple and Google promise that the kinds of inferences they will make from all of our data will be done in a differentially private manner. So this is a very solid and beautiful mathematical definition that has lots of nice properties that I won't have time to get into. And it's a subject of active research even now that many people at Penn are doing. Okay, that was the bad, the loss of privacy. And let's talk about unfairness that can arise from data, from machine learning algorithms used on data. Because automated decisions now impact very serious aspects of our life. For example, college admissions, maybe not so serious, but somewhat serious. Loans, bank loans, that could be more serious. Jobs, and probably the other ones are more serious still. Prison sentences, where to deploy police, and parole, all kinds of things are decided, or at least machine learning is in the loop on the decisions about lots of these things. Machine learning recommends a certain decision. Sometimes that decision is directly implemented. Sometimes a human will listen to the machine learning algorithm and decide. And so again, there was a lot of hype about this in the last several years, 5 years. Seemingly hiring and recruiting seem like some things that are very subjective and human-centric, but there were machine learning algorithms and many startups that started helping with these hiring decisions. And you can see some of the names here. Lending bank loans are also being done better by algorithms in some cases. And this is actually a Penn colleague in criminology. This guy trains computers to find future criminals. So the idea is to look at your record and predict how likely you are to commit a crime in the future. It's a little bit worrisome, but he's actually working with the Justice Department at various levels of government to try to make this happen. And sentencing is the other thing I mentioned about, like whether a person is likely to commit another offense if they're released affects how long the sentence should be. And machine learning algorithms are being used to predict how likely someone is to commit a crime again. Then predictive policing, where to send police depending on where crime is likely to happen, are all being informed at least by machine learning. But while all this good stuff seems possible, there's all kinds of negative sides as well. There's fear that it's triggering discrimination because we don't understand why the decisions are being made the way they are, whether they're using the right data. And there's articles about math being racist, and it's increasing the inequalities in various countries, in the US in particular, and talk about algorithms discriminating on admissions and various other settings. A beauty contest was judged by AI, and it was clear that the AI discriminated against dark skin, according to this article. So there's all kinds of potential ugliness associated with machine learning for decision making, especially critical ones, maybe not the beauty contest. One needs to, as computer scientists, it's our responsibility, since we are the only ones who really understand the technical side of this, to try to see that our algorithms are fair, or to understand what could give rise to unfairness and how we might go about fixing it. So let's ask ourselves, why might machine learning be unfair? There are many reasons, and here are some of them. One is data might encode existing biases. So what do I mean by that? Think of that bank loan officer example that we saw right in the beginning of this talk. Suppose that loan officer had a bias and really did not like lending to women, let's say. So just discriminated against women and was lending more to men than to women. Maybe even deserving women were denied. Now the machine learning algorithm is watching the bank officer and wants to copy the kind of rule that they were following. So what it will do is replicate the same bias and in fact amplify it, because it's going to be used all over the place. So if society as a whole has a bias against, say, women in some cases, or against African Americans or whatever, that bias will be amplified by machine learning if we don't recognize that it exists in the data on which the algorithm is trained. Another way data might encode existing biases is if we capture the wrong features. Suppose as a way of telling if a person is likely to commit a crime again, we use as a feature, was this person arrested before? Or how many times was this person arrested before? Now that's a bad sign, because some people are arrested very often just, I don't know, because of the neighborhood they live in or something like that, where the police are very active, and they're never convicted. I mean, so they're never guilty of anything, but just the fact that they've been arrested many times will now tell the machine learning algorithm, well, maybe they should be arrested again, because they're dangerous. They've been arrested a lot of times. So it's a self-fulfilling kind of prophecy. When you use the wrong features, you can sort of propagate this discrimination that exists already. So that's one reason. Another is that different populations may have different properties, and I'll show you an example in a minute. So you cannot apply the same rule for all the populations. So you might think that one could be fair by ignoring gender or ignoring race. So maybe the machine learning algorithm should not use race at all or should not use gender at all. That turns out not to be particularly fair either. So sometimes you have to actively use the gender and race in order to be fair. So we will see an example. I'll show you a small toy example in a minute. And the other problem is, as I said, machine learning algorithms work well when there's lots of data. And by definition, there's less data about minority populations than about majority populations. And so they don't understand the minority population as well as they would understand the majority population. Okay, so let's talk about different populations. Oh, sorry, one last example. Boston introduced something called the street bump program, which was seemingly a very smart, tech-savvy idea of trying to identify potholes in the city. What they said was participants in this program just downloaded an app called Street Bump on their smartphone. And then as they were driving around the streets, if they ever hit a pothole, the accelerometer in their phone would send a signal to the city saying they just hit a pothole. And then the city would see where the most signals were coming from and then try to go fix those potholes. Seems perfectly good and fair, does it? Well, it turned out, and this was recorded in the data, that most of the complaints for pothole fixing came from the affluent suburbs of Boston, affluent areas of Boston, and not from the poorer areas. And why is that? Well, there were fewer people driving with smartphones in the poorer areas, and therefore they didn't get as many complaints. So what seemed like a perfectly fair solution had this sort of hidden element of unfairness that was unintended, but it was there nevertheless. So that's common of many unfairness, situations of unfairness. It's not intended all the time. Sometimes it's not, but it's just, it happens. Okay, so talking about different populations with different classification rules or criteria, imagine this graph I've plotted of students, let's say, that SAT scores are on the y-axis. On the x-axis is the number of credit cards their family owns. It's a measure of how affluent their family is. And the plus signs indicate particular students who are going to do well in college, and the minus signs indicate particular students who are going to do badly in college. This is for a population one, let's call it the green population. Now, if a college wants to decide whom to admit, based on this knowledge, they would just find the classification rule, and let's say the classification rule is a line. They would find this blue line, and it's a pretty good classification rule. You can see that anybody above that line, by and large, is plus. There are a few minuses, and most people below the line are minus. So that's a way of classifying the green population. Now let's consider a less affluent population who perhaps didn't have the money to hire SAT tutors, for example. So it's a minority population, so there's fewer points. And you can see they're all shifted somewhat lower down. They have lower SAT scores and lower number of credit cards because they don't have SAT tutors, say. So the best classifier for them is this purple line. Now, if you look at both sets of data together, what do you think is the best classification rule? Well, if you look at the classification rule as maximizing accuracy, getting the positive points all on one side and negative points on the other side, you don't care about the orange points so much because there's so few of them. You try to find the rule that works best for the green points, so you go back to the rule that works for the majority population. And look at the effect it has on the minority population here. It classifies all of them as negative, and that's not good. Basically, they're qualified people who are not getting into college because of this uniform classification rule. So we need to take, in these cases, you need a classification rule that takes into account the particular groups that people belong to, gender or race or whatever. So we need two classification rules in this case. So again, to be fair, the algorithm may need to explicitly take into account the membership in various groups. Otherwise, optimizing accuracy just fits the majority population and does not fit the minority population. Okay. So notions of fairness that are around, individual notions of fairness. So this is kind of the ongoing research in fairness. How do we mathematically define fairness? Just like we define differential privacy as a notion of privacy. Individual fairness notions take on two flavors coming from philosophy. One is the idea that similar people should be treated similarly. And what similar people means, I don't have the time to get into, and what being treated similarly means. But that's a general goal where you want to be fair to every individual. And another notion of individual fairness, sometimes called meritocratic fairness, is that more qualified people should not be less preferred than less qualified people. Makes sense? So the more qualified student should have at least as much chance of getting into college as the less qualified student. And that also makes sense. Again, how to define these quantities, there's a lot more work going on about that. But if you don't want to focus on the individual level, you can also look at groups defined constitutionally by race, gender, disability, various other things. One notion you could have is demographic parity, which says that the fraction of people admitted from each group is the same. Let's think about college admissions. So the fraction of people admitted from various groups, women admitted is the same as the fraction of men admitted of all the applicants. That's a bit crude. It doesn't actually capture the qualified aspect of people. Equality of false negatives says that the fraction of qualified people rejected is the same. So that's the worst thing that can happen. A person is qualified to be in college, but they don't get in for some reason. So that's called a false negative, meaning they were good, but they're rated as negative. And we want the fraction of people who suffer this fate to be equal in every group. And that makes a lot more sense. You can talk about equality of false positives. And then a more complicated notion is something called calibration, which is whatever score the classifier gives to an individual, that score should be meaningful in some sense. And I won't go into the definition of that either. But these are the kinds of issues. We're working with various definitions, how to achieve these definitions in various scenarios, how to design algorithms that do that, and so on. So that's the ongoing work at Penn. Penn has one of the strongest research groups on both privacy and fairness. And we have a number of research directions. I think these slides will be out, will be available to the students, right? Or we could make them available.
Yeah. Well, certainly in the recording.
In the recording will be available. So I won't read these out, but these are some directions that we're going. So time for me to stop and maybe you have a couple of questions.
Yes, yes. So thank you so much, Professor Kannan. I know that I myself have questions, but I'm gonna ask you those later. So if you just look over here, 1, 2, 3, 4, 5, and there's the number 5, part 2. So those are some of the questions that have come in so far. So if you're interested in answering any of those, we can read them out loud.
Wow. So okay, let me start with the first one. The first one is, what is the minimum amount of data to somewhat guarantee the success of machine learning? That is probably impossible to give a number in a very general sense. It depends on the specific learning task you have, how complex the true classifier is, how many dimensions the data lives in, like how many attributes does each person have that are relevant. All of that has to be taken into account. So I cannot give you a minimum number like that, unfortunately. There are very theoretical toy scenarios where we can talk about this minimum number, but not for the kinds of applications I talked about. Yeah. And then by this logic, do you think that countries with stricter privacy laws, for example, USA, will have a disadvantage of developing machine learning versus other states, example, China? No, I don't think so, because we can still develop the machine learning algorithms. We just have to add a privacy layer. And we can, now that, for example, Europe has passed some very strict privacy laws called the GDPR, and the world is probably moving that way, maybe it will be required of any machine learning algorithms to protect the privacy. So we will have a tech advantage, I would think, if we are able to design machine learning algorithms that are private. Right. What would be the main ML technique used to build the predictive models for admissions, loans, policing, etc.? Is it just ANN? Yes, by and large, it's artificial neural networks these days for most of these tasks. Earlier, it used to be some linear classifiers and some more simple things, but by and large, now we have, the more data we have, the more tempting it is to just resort to throw all the data at the artificial neural net and hope that it produces a good answer. But even there's some design decisions about which particular ANN to use. So yes. So can you discuss about the biology, the major challenges of machine learning in biology? Okay, so yes, there are lots of interesting challenges in biology. For example, understanding even just what regions of the DNA molecule represent what function in biological terms is an area in which machine learning comes into play. For example, which stretch of the DNA is a gene beginning? What are the parts of the gene it at various places. This is often, machine learning is a big help in answering these questions. Another type of question that machine learning is one way to attack is, what is the structure of a protein molecule? How does a protein molecule fold into a three-dimensional shape so that it can do whatever it's supposed to do as its function? So this is, while there are some traditional algorithms for this problem, now machine learning is also used here. I mean, every place you can imagine machine learning is used, even understanding ontogeny, the process of development, and the cell division that goes on in ontogeny. There's some work going on at Penn that I'm talking to the researcher on, which tries to use machine learning for this work. So it's everywhere in biology. Decisions can be made by purely by machine learning results. Do you think in the future the combination of complex sets of rules and several machine learning scores will fit in the majority scenario, like in the financial service right now? I mean, I think we will never get to the point where machine learning can be let loose, or maybe never is a strong word, with completely no supervision by humans. It may be that human sort of checking up on the machine, oversight of the machine learning algorithms can become less and less frequent as we trust them more and more, but we are far from trusting them right now. So I think for any critical decision, I would, for example, recommend that there's always a human in the loop, and this is not done entirely by a machine learning algorithm.
There's more down here. We have a couple more minutes if you're
okay.
willing to answer.
Let's stop with number 8, shall we? And then there are 8 questions here, and then we can take over. Yeah. So how can data retain the human element while still being effective? Is it correct to say that in order for data to be effective, the human aspect needs to be minimized? If this is the case, is the data being used in favor or against the public itself? That's a great philosophical question. I think there are certain aspects of humans that we want to amplify, and certain aspects of human biased decision-making and stereotyping and so on that we want to minimize, right? So we want to capture the wisdom of the human beings, but remove the bias of human beings. And that's the challenge, really. Human beings are not perfect, but a pure automaton which does not take into account sort of human ways of valuing different decisions is not going to be great. So we need the kind of moral, ethical principles that humans have derived over the centuries to be imbued into the machine learning algorithm. And that's the challenge, doing that without incorporating some biases as well. I mean, some of these quote unquote moral principles have been cloaked to defend horrible, immoral practices. I mean, the Nazis had probably a moral principle about, how they were behaving. And so we want to question the moral principles on which humans have been making the decisions, and machine learning algorithms will, but we don't want to throw away, centuries of philosophical thinking or legal thinking on what is morality, what's a moral decision to make. So we definitely want machine learning algorithms to have that as well. But that's the kind of thing where computer scientists cannot go alone. We need to talk, and we do talk to philosophers, legal scholars, social scientists to try to understand this in a holistic manner. Picking the right features are critical to be accurate and ethical. In order to find the most relevant features, do we need to keep doing linear regression for others separately, or we can build it as an inherent part of the ML model itself? If ML has the way to improve selection more objectively, is there hope we can automate at least some feature selection? Absolutely. I think that's a good question. And I think there's already some ML algorithms that partially sift through the features that they have and select which ones are the most relevant. I mean, there's something called principal component analysis, which looks at a data set which has lots of features and identifies which features are the most informative. A small number of features are the most informative on the data, and tries to work with that data, work with those features. So yes, there's definitely hope for at least partial automation of the feature selection problem. But again, humans have to be involved to see if the results being produced are exactly aligned with what would be morally acceptable. And lastly, are there examples of machine learning applied to non-human settings like climate data? Absolutely. So climate prediction, prediction of resource use, or even nowadays, population projections of the world. Like, that's human, I guess. But climate climate is certainly one of those areas where machine learning is a huge player. I mean, it predicts, it forecasts into the future, potential weather conditions in different parts of the world, and therefore extrapolates on that and gets the climate predictions. Yes, climate prediction, climate is a very inexact science, as you probably know, especially the further out you go, the less accurately you can predict. And so machine learning it has made some starts at it. It's not wonderful at it, but it's probably as good as any other method we know for predicting some aspects of the climate in the future. Okay, I'll stop here and let you.
Well, we're having even more questions for you come in, but I know it's like so fascinating. We could just keep going. There's one here that's relevant. Is there a course related to this in the program?
There will be a course on machine learning right away, which will have to start in January, we think. Yes, sometime by the time you get to electives, a course on machine learning will exist. And then there'll be a course on ethics in data science, which will talk about privacy and fairness. So my talk covered sort of aspects of both these courses. So there will be two courses that sort of elaborate on different parts of this topic.
Yeah, so basically once you get through kind of the 6 core courses, which we'll go through briefly, then yes, you will be prepared to take electives on topics such as this. Mm-hmm. So thank you. I'm going to quickly switch to another presentation. So just bear with me while I get that one started. And then we shall talk about admissions. Okay, so back here. And share. Okay, so let me just briefly tell you about our degree program. MCIT is a Master of Computer and Information Technology. It is not a Master of Science. It is a different credential. But when you finish it, you will have the same type of knowledge as someone who has a Master in Computer Science. Master of Science in Computer Science. It has already existed at Penn for 17 years on campus, very successfully, and it is designed for people who do not have a CS background. So basically the qualification is that you have a bachelor's degree in any area, except for computer science, because in that case, you would just go for a regular computer science master's.
And you would be considered overqualified for the MCIT program.
Yes, exactly. Yeah. So students in our program, and we have some now, we have students who started in the spring who are doing a great job, and they will graduate with a diploma from University of Pennsylvania that has no mention of online on it. It's the same degree program as our on-campus program. It has the same name as well. So just briefly, this is a summary of the curriculum. I referred earlier to 6 core courses, and these are the first 6 courses that you would take in the curriculum. You would take them sequentially, and they have different relationships to each other. They build upon each other, but then also some of them are more coding related, some of them are more math related, some of them are a little bit more theory oriented, some of them are a little bit more hands-on. But by the time you get to the end of the 6 core courses, you are basically ready to take on a lot of different types of topics. What's really neat about our program is that you don't just learn 1 or 2 particular coding languages. You learn to understand what a coding language is at its core and the theory behind it, so that you will be able to teach yourself any language moving forward. So as you know, technology moves very quickly, and there might be one coding language that's very hot right now, and we could teach you that, but what we're actually doing is going farther than a boot camp or something like that, and teaching you the fundamentals so that you have the problem solving tools and the ability to teach yourself to be agile and deal with whatever problem comes up. So then you have 4 electives. You can see we haven't finished creating all of them yet because our program is so new, but We design them based on the most popular areas of interest, including machine learning. And then we're also, we have polled our current students, and we'll continue to do that for a while, on what they're interested in learning about. So that's one perk of getting in to the program earlier on, is that you will help us shape the future of the program. So this is kind of a flow with some details. There's more, just so you know, there's more details about all of this stuff on our website, which is onlinelearning.cs.upenn.edu, and I'll ask my team to paste that into the chat tool. But this is kind of an overview. It shows you the basic fundamentals of what you need to submit with the application. As you can see, the GRE is optional. If you're able to take the GRE, we do appreciate that, in terms of it's sort of a concrete measure of your quantitative abilities, but it is not required by any means. So we also don't need your official transcripts unless you've been admitted to the programs. However, when you're applying, we do need to see all of your unofficial transcripts from any kind of academic credit that you've received containing a grade. The early admissions deadline has passed, so you can skip over that part for now. And the regular admissions deadline, which is the final deadline for students starting in the fall, is May 1st. So that is the final deadline. And what I will point out is that we need to receive by May 1st. So perhaps you have gone onto the online application and filled out your whole application and pressed submit. That still actually is not considered complete for us. We would not evaluate it at that stage, because we need a minimum of 2 letters of recommendation to evaluate, and also potentially your official English proficiency details from the testing facility, if that's something that is required for your application. So again, the details are on our website, but all that to say, aim to get it in as soon as you can if you're interested in starting in the fall. And another tip I have is to ask 3 people for a letter of recommendation, just in case one person falls through, or life circumstances prevent them from submitting it. Then you'll at least have the minimum, and you'll still get reviewed. Classes start August 27th, which is gonna be here as soon as you know it. This slide is about program pacing, and there are a lot of different speeds that you could take our program in. There are 10 courses total, as we mentioned earlier, and the next slide will be about tuition, so I'll talk about that next. But this is one sample schedule where a person takes 2 courses every semester, including the summer, and that could be completed in 5 semesters. So Penn has, summer is optional, but core courses will always be available in the summer for our students. You could do a lot of different combinations depending on whether you're working full-time or not. If you wanted to take 1 course per semester, you could do that. If you wanted to take 1 course in the fall and then 2 in the spring, because your workload is a little bit lighter then, and then take off the summer, but then next summer maybe you want to catch up and you take 1 course then. All of that is possible and very easy to do. You would vacillate between being full-time and part-time depending on how many classes you take, but there's no paperwork that needs to be filled out. The only situation you would need to fill out paperwork is if you want to take a leave of absence, which is also possible. And in that case, you can take up to 4 semesters off, essentially total, not including the summer. Summer is always optional. But if something's going on at work, or something crops up in terms of a health issue, and you need to take 1 or 2 semesters off as a leave of absence, you would submit a form, and that's not a problem typically either. So this is the slide about the tuition and the fees. So the total tuition is $25,000. That's about 1/3 of the on-campus price. There's also a course fee, which is $130 per course. So at Penn, we charge per course. So you never pay the full tuition on the first day. You would only pay tuition per semester based on how many courses you're taking that semester. So you can see in the chart, if you're taking one course in that semester, the total cost would be $2,630 based on the combination of tuition and fees. If you're taking two courses in a semester, scales up, obviously. And then I'm going kind of quickly because I want to have time for lots of questions. Yeah. So I think our questions start around
one there.
Here, and let's just skim through quickly and see. I can answer three very quickly.
Okay.
What is the maximum amount of months given to complete the master's program? The answer to that is 7 years. So you can take up to 7 years to complete the program, which is the same rule as our on-campus program, coincidentally. Yes, and how do classes work with unpredictable work schedules? Well, I think I sort of referenced that in terms of if you need to take a leave of absence, but let me just quickly address what it's like to be a student in a semester in our course. So typically how it works is many of the video lectures will be released on the first day, half or all of the class. So you'll be able to watch the video lectures. However, the assignments are typically rolled out at a 1 to 2 week basis. So all the students would be working on the same assignment at the same time. If you wanted to watch videos ahead of time, just because you are anticipating some travel or something, you could do that. But in general, of course, the students kind of work on things together on the same pace. Now, that being said, again, all of the videos are available for you to watch on your own schedule. There are no required synchronous sessions. So that means there's no time where at 8 a.m. Eastern time, everybody has to be doing a certain thing. There are only windows of deadlines. So perhaps there's an assignment that's due within, a 24-hour time frame, or maybe there's an exam that you need to complete, in a 5 to 7 day time frame, something like that. So,
but just to elaborate on that point a little bit, there are no required synchronous times, but there are some synchronous activities that do happen, which are optional entirely. Like many courses have what's called a recitation, that's what Penn calls it, where students get TAs lead students through examples to elaborate on concepts they've seen in the lecture videos. So that's one thing that's synchronous. Office hours are synchronous as well, right? So, but other than that, there are no required synchronous activities.
Yeah, we certainly have a lot of optional support in terms of private and group office hours that are in real time, but you can, basically the schedule is laid out and you can pick a time that works for you. So let's see what other questions. I can quickly answer number 9. What is the length of each core course? That is, our program follows the same academic schedule as on campus. Maybe you can look and see which one you would. Okay. Yeah. So again, we have 3 semesters. So the fall and spring are about 14 weeks plus 1 or 2 weeks for final exams. And then the summer semester is condensed. So that everything is condensed into 11 weeks. So that is a much more condensed schedule. And sorry, I forgot to answer a question. I'm remembering there was one about military financial benefits. And MCIT is on Penn's list of approved programs at the VA. So future online students should be eligible for VA educational benefits. And I think there's more details in the Q&A box. So just so you know, our team is recording some of these answers that we've said out loud and adding even more information within that Q&A tool. So if you click on the A part, you'll actually see an archive of all of the questions that have been answered so far. And you can use that as a reference. But we do have more, we have a very extensive FAQ section on our website with a pretty robust search engine. And we have more specific information about veteran affairs within our FAQ.
Okay, let me answer number 10. How would you describe the program's big differentiator to other similar programs aside from the online component? What sets UPenn's program apart academically? Well, first of all, our online program, our goal is to match it exactly to our on-campus program. So the curricula for all the courses are identical to what we teach online. The faculty teaching the online courses are identical to the faculty teaching on campus, at least related courses. And maybe the biggest differentiator is that we are not looking to create a mega big program. We are creating a smallish program as online programs go, with the idea being that we want to have a high touch program with a kind of student to TA ratio that would make it easily possible for you to get help on any material that you need help on. So I think right now our classes have a ratio of 25 students or so to a TA, roughly speaking, 25 students.
Yeah, maybe
even less than that, maybe 20 to 1 or something like that. So that's a huge differentiator, so that you're not off by yourself, but you're getting a lot of help. And of course, Penn is an Ivy League place, and so we also pride ourselves on the fact that the quality of the faculty here is really great, and we're doing sort of the most cutting edge research in every area that this program covers, and so our teaching is also informed by latest developments and things like that. So that makes, that's one of the properties of this program.
Number 7 is, I have a question about specializations. Does the MCIT program offer specializations, for example, in data science? We will not have, another word for that would be concentrations. The program does not have that. And I can't give any more information about those courses because, like I said, our program is so new, we're still creating them. But the idea is to have over time a robust list of topics and electives to choose from with details.
I would say data science is high on our priority list, and I even talked to a faculty member today who might be interested in teaching a data science course. And the reason we don't have concentrations is that we only have 4 electives. You have 6 core courses. So I think it's probably wise for most people to spread those 4 electives out across a variety of topics rather than concentrate them in one area. So it didn't make much sense to have concentrations.
This is a big one. What is the significant difference between enrolling on campus and online? I know the tuition is more affordable online, but does that mean that online students have fewer benefits to expand their network? Will there be a way to connect to professors? Will there be chances for students to have live discussions? I can talk to that, but if you want to
go right ahead, start first.
Yeah. So, in terms of student services, the fee that the online students pay is again lower than what the students on campus pay, and so the student services are fewer than what you would receive on campus. However, we still want to make sure that the essentials are provided, and so career services is included in the services that you would have access to. And actually, when we polled our current students, don't know if you can hear that helicopter, we polled our current students, networking was very high on their list of interests. And so, we will be providing that through a combination of program level initiatives, school level initiatives, university level initiatives. Networking, I would say, we are very solid on, because if you become a student in this program, you can obviously have your fellow MCIT online students as networking colleagues, but then you also have access to the entire University of Pennsylvania alumni network as soon as you become a student. You don't have to wait till you graduate. That happens right away. So I think that in and of itself is pretty remarkable. And actually what's fun is that there are alumni clubs, I guess you'd call them, around the world that Penn has. And as current students, you can show up there to any events that are going on. And that could be like an in-person type of experience.
So I just wanted to add something from the access to professors point of view. When we set out to make the online program identical to the on-campus program, we asked ourselves, what is our yardstick for saying, are the faculty interacting with the students as much online as they would on campus? And we said to ourselves, maybe a measure would be, recommendation letters. So a student who is on campus, who's taken a class with the professor, certain students, if they've done well enough, feel comfortable to ask the professor for a letter, and this professor agrees to write that letter because they know the student sufficiently well. We want to ensure that online as well, again, students who take a class and do reasonably well will be able to get letters from the professor. So we are aiming for the level of contact between professors and students that gives that degree of familiarity to the professor.
Yeah, I think we won't necessarily be able to guarantee that for
in
every
the beginning.
single person.
Right.
And so we're working towards it.
That's right.
I think this is a good one to end on, maybe number 15, you could speak to.
Yeah, what job roles are likely won with an MCIT degree? So essentially, again, Olivia said earlier that the MCIT degree gives you the same qualifications as a master's degree in computer science. So our MCIT students have gone on to work at the same tech firms that our Masters of Computer Science students do, which is the usual suspects like Facebook and Google and Amazon and Twitter and Airbnb and Uber and all these companies as well. But they've gone on to work at startups, some of them as well. And some of them have gone off to sort of financial world, being analysts. So technical education surprisingly prepares you also to be in the financial world for some reason, because they want the kind of logical thinking that a computer science education gives you. So our MCIT students basically occupy the same sort of spheres as our MSc students, I would say.
Yeah. So thank you so much for attending today. And I hope you found something useful here. But if we didn't get a chance to answer your question, I wanted to point out some of these other resources. So I mentioned before on our online learning.upenn.edu website, there's a whole section devoted just to the MCIT online program, and the FAQ database is pretty robust. Then again, if you don't find your specific question there, you can email us. I'm one of the people who might answer your email at online-learning@cs.upenn.edu. And we generally pride ourselves on a pretty quick turnaround there too. So if you are interested in learning more about our program, perhaps if we have future webinars, maybe you're not ready to apply today, but I think it would be fun to have more webinars that contain interesting research, such as the one we had today. You can
let us know your opinion on that, whether it's useful to have that or whether you prefer the straight-on discussion of the program itself.
Yeah, exactly. So you can join our mailing list, which is on the Coursera website under bullet number 3. You can also just Google Coursera and MCIT online, and there's a big button that says request more information. And then lastly, I just wanted to mention the 4-week course that we have on Coursera, which is open to anyone. It's $49, and it's called Computational Thinking for Problem Solving. And it was created for many reasons, but if you're a person, like for myself, I was a theater major as an undergrad, but I thought, well, I did take a math course and I did pretty well. I wonder if I might have any quantitative ability. This course would be for you. It's designed for people, again, without a computer science background. It's 4 weeks, and it really slowly takes you through the steps of what does it mean to think in this different type of way, more like a computer. And by the end, you actually program a little bit in Python. I'm planning to take this course. I haven't done it yet, but we have had a lot of good feedback about it. And there's a couple good things about taking this course. One is that for yourself, it might give you a good idea of whether you enjoy this content or not. Another is it's taught by one of the other program director for MCIT Online, Chris Murphy, who will also be an instructor within the core courses. So you can see what it's like to learn from him. And you can see the production quality. that typifies our courses.
Mhm.
I will say, let's say you finish this computational thinking MOOC and you say to yourself, wow, that was easy, no problem, I'm going to apply. That's great. And just know that the actual degree program is much more accelerated and very, very much more difficult than this particular course. So while it gives you a sense of the type of thinking,
it's a gentle introduction.
It's a gentle introduction, and if you think about it, because our degree program is trying to bring people up to speed, it's almost accelerated, I would say, in terms of the curriculum. The 6 core courses move very, very quickly, and so can be an adjustment. But I would say, too, if you take the computational thinking for problem solving course and you apply, please mention it, because that always helps us in terms of, oh, look, this person, passed this course and has some experience now with online learning on the very same platform, Coursera, which is where our degree program is hosted. So it's looked upon favorably in the admissions committee. So I think we're going to sign off now, but
lots of good questions we didn't get time to answer, but that's
yes,
where it goes. Yeah.
Yes. But thank you again for joining us, and have a great day. Bye.